Welcome to the problem-solving session for Chapter 26. We begin with Part 1. Question 1 gives us a capacitor that is filled with Teflon as the dielectric, and it's a parallel plate capacitor, each of which has, let's get our pen here, an area 7.6 e to the minus 4 meters squared, with a distance of separation 1.8 e to the minus 3 meters, and the 24-volt battery is used to charge this capacitor. So, first question is, determine the dielectric constant. Well, the only way we can do this is to consult our textbook and look up the value of kappa for the dielectric constant of Teflon. So in other words, if this was the first question, if this was a question, let's say, on a test, for example, if I give you no other source of information, I would certainly give you the value of kappa. Anyhow, next one. Determine the electric field magnitude between the plates, because of course we know that the direction of the electric field is from the positive to the negative. So the magnitude of the electric field, if you recall in Chapter 25, is given by the potential difference between the plates divided by their distance of separation. Well, 24 volts divided by 1.8 e to the minus 3 meters gives a value of 1.33, and of course the 3 repeats infinitely, e to the 4 volts per meter. So, provided that I entered my numbers incorrectly, the magnitude of the electric field is 1.33 e to the 4 volts per meter. What about the surface charge density? Well, here, if you recall, the surface charge density is given by the ratio of the charge on the plates divided by area, but we don't know the charge yet. How about this? Do we recall from Chapter 24 that for any conductor in electrostatic equilibrium, sigma divided by epsilon naught was equal to the electric field. So in other words, we saw the electric field for any capacitor in electrostatic equilibrium was sigma over epsilon naught. Okay, well, how about this? Suppose that we do not have vacuum between the plates, because if you recall, this is the permittivity of free space. But our space is no longer free. Our space is filled with Teflon. So the value here, epsilon naught, is no longer representative of the material that separates the plates. In fact, to make it so, we have to multiply the permittivity of free space by the kappa for Teflon. And that combination, that product, is what gives us the epsilon naught, the permittivity of Teflon. So, here, if we substitute for sigma, we can then, in this expression here, we can then write that sigma equals electric field magnitude, what we have just obtained in Part B, times kappa times epsilon naught. And so this, since we know kappa, we know epsilon naught, we know magnitude of electric field, this certainly gives us a method for calculating sigma. And if we entered all our numbers correctly, we get a sigma, which is 2.47 e to the minus 7 coulombs per meter squared. Okay, Part D, next question, asks us to determine the capacitance of this capacitor. Well, we can again obtain the capacitance as the ratio of Q over delta V. But since we don't have Q directly, how about if we obtain it by taking kappa times epsilon naught, multiply that by A over D. In other words, if you recall, kappa times this ratio epsilon naught A over D is how we had defined the capacitance of any capacitor. Well, of course, our kappa is 2.1. Epsilon naught is 8.85. E to the minus, 8.85 e to the minus 12. A, 7.6 e to the minus 4 meters squared. And D, 1.8, 1.8 e to the minus 3 meters. That gives us a value of C, which is 7.847, or rather let's go ahead and use our little eraser and round it to 3 significant digits if we choose to. 7.85 e to the minus 12 farads. Next question asks us to determine the charge on its plates. Now here, of course, as soon as we have C and we know that our delta V is equal to 24 volts, we can use this expression to solve for Q as C times delta V. And when we take the value of C we just obtained with our delta V of 24 volts, we get 1.88 e to the minus 10 coulombs. Could we have obtained this Q as the product of sigma times A? Because after all, sigma represents the density of charge over the given surface area of the capacitor. Would this also have given us the same number? Why don't you go ahead and verify that, and in the meantime, I will go ahead and say, yes, indeed, when I plugged in my numbers, that is exactly what I got. Last part says, what is the net charge of the capacitor? And this is like a freebie. Of course, we know we've got minus 1.88 e to the minus 10 coulombs in the negative plate, positive 1.88 e to the minus 10 coulombs in the positive plate, and if we add them up, we get nothing but 0. Next question. Here, we're asked to derive an expression for the capacitance of a cylindrical capacitor, given that from chapter 24, we got an expression for a cylinder or a very long line of charge using Gauss's law as lambda over 2 pi r epsilon naught. And of course, our lambda here is Q over L, right, in one dimension, over the length of the cylinder. And we can also write here, how about this? If we multiply numerator by 2 and denominator by 2, we end up with 4 pi epsilon naught in the denominator. This can be written as K times 2Q divided by R times L. Okay, also from chapter 25, we know that the potential difference between the plates, in this case the plates of the capacitor, or any 2 points, let's say the point A, the radius of capacitor 1, point B, the inner surface of capacitor 2, is given as the negative of the electric field times dr. So we are going to use this expression further because after all, to get C, we're going to make use of Q over delta V. So we want the delta V that corresponds to this capacitor. And what I'm going to do is I'm going to take the expression for E here, K 2Q over RL, and because the electric field is already radial, the R hat has a magnitude of 1, dr vector has a magnitude of dr, times the cosine of 0 just gives us dr, and so here dr of our integral. Now the potential difference is between the points A and B, where A is the radius of the inner curved surface of the cylinder. Little b is the outer surface of the inner cylinder, and B is the inner surface of the outer cylinder. Boy, that's a mouthful. All right, well, let's go ahead and pull out our constants out of the integral K 2Q over L, and we are going to take the integral of dr over r from A to B. Well, what we get is we get an expression here that the integral is given as the logarithm, the log of, see, this was b to a, the log of b minus a minus the log of a, which gives us ln of b over a. And of course, once we have delta V, now let's go ahead and just rewrite it here. If we have a negative sign here, we can just switch this around and write the log of A over B with that negative sign. So K 2Q over L times ln of A over B. Now we come back over here. C is equal to Q over delta V. Delta V is K 2Q divided by L times ln of A over B. The Q's cancel, and we're left with an expression of L divided by K times 2 natural logarithm of A over B. So pretty much what you can see here is that the capacitance, therefore, depends on how long the cylindrical capacitor arrangement is. And of course, each of these would have the same length, like in the case of the parallel plate where each has the same area. Here, each cylinder making up the capacitor would have the same length, divided by the natural log of the ratio of the radius of the inner cylinder to the outer cylinder. What about the spherical capacitor? Can we do the same and obtain an expression for the capacitance? The answer is, why not? And we once again begin with our delta V expression here, where delta V is the negative of E dr, where again E is radial, so we know that the scalar product of r hat with dr vector is just dr. So we write our expression for E, which is kq over r squared, and we know this from Gauss's law, where we take a Gaussian surface and we surround the inner sphere, and we look at the fact that the charge on the inner sphere is q. And so this is a very familiar expression for us. We factor out delta V minus kq over r squared. Oops, Can't factor out the r squared because our r squared is constant. So let's go ahead and write this properly. Minus kq integral of dr over r squared from a to b. Okay. Now, the integral of dr over r squared is minus 1 over r. And so minus 1 over r from a to b with this negative sign here becomes kq times 1 over b minus 1 over a. So delta v depends on the reciprocals of the radii of the conducting spheres that make up the capacitor arrangement. And once again, C equals Q over delta V. So we write Q over KQ, 1 over B minus 1 over A. The Q's cancel. And so therefore C is 1 over B minus 1 over A divided by K. And only depends directly on the radii. We can clean this up algebraically if we wanted to find a common denominator, etc. But the point is that the capacitance only depends on the inverse of the, in this case, subtraction, if you like, of the radii. Next question. Question 4 gives us two capacitors arranged in a parallel form. We have capacitor 1, 4 microfarads, capacitor 2, 6 microfarads, and you can see that it's parallel because the positive terminal of the battery here connects to both C1 and C2. The negative terminal connects both to C1 and C2. And we're asked to determine several quantities. So let's begin. In part A, we're asked to determine the total capacitance. Well, because these are in parallel, we simply add C1 plus C2 and we get 10 microfarads. Part B asks us to determine the total charge of this arrangement. Well, if we knew Q1 and Q2, we could add it up and get the total charge. Since we don't know the charge on each individual capacitors, we're going to make use of the expression that C total, which we now know, times delta V total, which is the potential of the battery, will also give us Q total. And so here, 10 microfarad times 12 volts gives us 1.2 e to the minus 4 coulombs. In part C, we're asked to determine delta V1 and delta V2. But again, since this is a parallel arrangement, we know that the potential difference between each of the plates in these capacitors has to equal that of the battery, which is 12 volts. Lastly, we're asked to determine the charge on each capacitor. Well, Q1 can be determined by taking C1, which we know, 4 microfarads, and multiplying by delta V1, which we know is 12 volts. This gives us 48 microcoulombs. Q2 we obtained using the same product, but this time C2 times delta V2. Well, C2 is 6 microfarads, delta V2 is 12. This gives us a value of 72 microcoulombs. Remember when we said that Q total was the sum of Q1 plus Q2, and our Q total was 1.2 e to the minus 4 coulombs? Let's see. If we took 48 microcoulombs and we added it to 72 microcoulombs, would we get 1.2 e to the minus 4? Check it out. We should get the same number. Next question. This time we are going to set up the capacitors in a series fashion. So we have C1, C2, C3. Notice here, well, we have a little degradation here on our picture, but notice that the positive plate of the battery only connects to the left, the positive terminal of the battery only connects to the left plate of C1. The negative terminal of the battery connects to what will be the negative plate of C3. But we know that charges are going to be the same as Q total. It's just that our delta V's are not going to be the same. So the first question asks us to determine C total. Well, since they are in series, we have to add the reciprocal 4 microfarad with the reciprocal 5 microfarad with 6 microfarad. In other words, 1 over C1 plus 1 over C2 plus 1 over C3. Well, one way to do this is get a common denominator, which here I'm going to choose as 60 microfarads, and I end up with 15 plus 12 plus 10, giving me 37 over 60 microfarads. Now I've got to take the reciprocal, C total equals 60 microfarads over 37. That gives me 1.62 microfarads. Part B, Q total, again, here, I don't know Q1, I don't know Q2. I'm going to take the C total, which I just calculated, and multiply it by the delta V total. The delta V total being that of the battery. Well, that gives me 1.95 e to the minus 5 coulombs. Part C asks for Q1, Q2, and Q3. Well, again, they're connected in series, so I know that the total charge will be the charge that each of the capacitors will store. In other words, they all carry the same quantity of charge. Lastly, to get the delta V's, the potential difference, I'm going to make use of the information that I have. Delta V1 equals Q1 over C1. When I take that ratio, I get 4.86 volts. Delta V2, Q2 over C2, I get 3.89 volts. Delta V3, Q3 over C3, that gives me 3.24 volts. Do these add up to delta V total, which is 12 volts? Check it out. My calculation says that they do. Well, this concludes the first part of the problem-solving session for Chapter 26. Until next time.